my name is Pamela. Welcome to my channel. Today I'm gonna talk about the galvanometric circuit is based on the deflection of a coil located between two poles of a permanent magnet as the current of the primary element passes through it. The passage of current produces a magnetic field that opposes to that of the permanent magnet, and the moving coil rotates until the corresponding magnetic torque is balanced by the tension torque of the spring. The pointer is rigidly attached to the voice coil and travels along a graduated scale. Temperature variations can influence the electrical resistance of the measurement circuit, and to cancel them, a negative temperature coefficient resistor, or NTC, called compensation resistance, is used, of which I talk about in the video of Thermocouples Part 1 that I left you in the eye. The connection cables to the thermocouple can also vary in resistance with temperature and affect the accuracy of the measurement, of which I talked about in my last week's video, Thermocouples Part 2, that I will also leave you in the eye. The potentiometric circuit consists of a constant voltage V that feeds the two arms of the circuit with currents I1 and I2. Here, the connected thermocouple T is connected to the lower arm E and to the rheostat R through a milliammeter. The position R of the cursor of the rheostat R indicates the process temperature when no current passes through the milliammeter. That is, when the point C of the rheostat cursor R and the point E are at the same voltage. By setting the rheostat, we would have a temperature instrument. However, this method is impractical, and a self-balancing device is incorporated into the circuit to replace the milliammeter with an amplifier. If there is a potential difference between the EMF generated by the thermocouple and the voltage given by the cursor of the rheostat R, the amplifier circuit will excite the balance motor until the position of the cursor is correct, position that represents the EMF generated by the thermocouple, and therefore its temperature. The potentiometric circuit is necessary to compensate for temperature variations in the reference junction of the thermocouple, which is done by means of a compensation resistor of the cold junction, which absorbs a voltage equivalent to the EMF that the thermocouple would have with the hot junction at the temperature of the instrument case, and with the cold junction at 0 Celsius degrees. The compensation system is not perfect, but it is accurate enough to meet the manufacturer's measurement precision. When an internal compensation is required, it is necessary to use external compensation boxes generally installed in the process and inside which is the reference junction. These boxes can be temperature controlled or can directly compensate for variations in ambient temperature. The circuit also has a resistance RD to protect against breakage of the thermocouple or the compensation wire. This resistance is of high value, and the current flowing through it causes a voltage drop that is added to that generated by the thermocouple, producing a shift of 0. This voltage drop is negligible and does not influence normal operating conditions. However, when the thermocouple breaks, the resistance RD closes the amplifier circuit enough for the rheostat cursor to move to the top of the scale and to trigger an alarm. If we add a microprocessor, we can obtain by hardware or software potentiometric circuits with different characteristics, as well as intelligent transmitters, prepared for the automatic measurement of temperature with different types of thermocouples or signals in millivolts, with compensation of cold junction temperature, with self-diagnosis routines, with linearization of the 4 to 20 mA DC output signal, and with galvanic isolation between the input and output, which allows the sensor to be grounded with high protection against noise. The microprocessor of the potentiometric circuit has in memory the tables of EMF temperature or the corresponding polynomial functions. Two cases can occur when measuring temperatures with thermocouples. 1. Checking the galvanic, potentiometric, or digital instrument. And 2. The verification of the EMF of the thermocouple. In checking the instrument with ambient temperature compensation, the The conversion tables of EMF are used. Refer to 0 Celsius degrees of the cold junction to determine the EMF in millivolts corresponding to the process temperature T and the EMF due to the ambient temperature TA, which is measured with a mercury thermometer placed next to the instrument. These EMF are subtracted, since under normal working conditions the instrument will receive the electromotive force V minus VA and will mark the temperature T corresponding to the EMF, since it has ambient temperature compensation. Therefore, generating with the millivolt generator potentiometer set EMF, the instrument should mark the temperature T, otherwise the instrument will be out of calibration. For example, we have a scale instrument from 0 to 700 Celsius degrees type J with ambient temperature compensation, and we try to check it for the temperature of 700 Celsius. We connect the millivolt generator potentiometer to the device, and with a mercury thermometer attached, we read 20 Celsius. These values are found according to the J-type thermocouple conversion tables. So, generating an EMF of 38,111 millivolts, the index or digital value indicating the temperature should be at 700 Celsius if it is properly calibrated. In the case of microprocessor potentiometers, the device has temperature compensation in the cold junction and has in memory the EMF temperature values for the different types of thermocouples or the polynomials of values of the EMF depending on the temperature. So it is enough to directly place 700 Celsius or 38,111 millivolts. Verification of the EMF of a thermocouple is done as follows. In this case, the generator potentiometer is connected to the thermocouple terminals, and there is a standard instrument connected to a standard thermocouple, which measures the actual temperature T of the process. A mercury thermometer placed on the other side of the potentiometer will give the ambient temperature TA. Using the conversion tables, the EMF or VP read on the potentiometer and the VA corresponding to the temperature TA are summed, since inside the potentiometer there is the cold junction, and the EMF read is less by a value VA than V that would be obtained if the cold junction were at 0 Celsius. For example, we have an iron constant type J thermocouple to check. When the potentiometer is connected, we have an EMF of 38,111 millivolts. The mercury thermometer on the box gives an ambient temperature of 20 Celsius. Consulting the conversion tables, we know that, in this case, you must have an EMF of 1019 millivolts at room temperature. So, the EMF that will generate the thermocouple with the cold junction at 0 degrees will be calculated in this way, which corresponds to 700 Celsius in the conversion table, and this is the temperature that the master thermocouple connected to the master instrument should signal. If it doesn't, the thermocouple may be faulty or old. The reasoning exposed in these two cases are based on the law of successive temperatures, which I explained in the video of Thermocouples Part 1 that I left you in the eye. And well, this will be all for today's video. Don't forget to give me a like, subscribe, and share. I upload videos every Wednesday in Spanish and every Friday in English. Adios! Using the conversation tables. Ay, Diosito. Ay, Diosito. Using the conversion tables. Morning.